From this lecture, we are going to start a new course, Digital Electronics. In principle, digital electronics deal with digital quantities. From your previous courses, you have come to know that electronic circuits can be divided into two broad categories. One is digital, another is analog. And digital electronics involves quantities with discrete values, and analog electronics involves quantities with continuous values. I will discuss more on digital and analog quantities later. Here, I want all of you to know that this course is very fundamental for the students who want to continue their job or research in computer design and robotics. However, digital electronics is applied in a wide range of areas in addition to computers. Such applications are communications systems, radar system, navigation and guidance system, military systems, medical instruments, industrial process control, etc., etc. Here we will concentrate on designing of digital electronic circuits. The course objectives and the course outcomes are given in the lecture plan. I have subdivided the complete course into two broad categories. One is combinational logic circuit, combinational logic circuits. Another is sequential logic circuit. Combinational logic circuits will be covered before the mid-semester exam. So before mid-exam, and the sequential logic circuits will be covered after the mid-semester exam. Next, the books. The books that I'm going to follow to cover this course are, these are the name of the books: Digital Logic and Computer Design by Maurice Mano. This will be our textbook, and all other books that you can see: Digital Fundamentals by Thomas L. Floyd, Digital Electronics Principles, Devices and Applications by Anil K. Maini, Fundamentals of Logic Design by C.H. Roth and L.L. Kinney, Digital Electronics, A Practical Approach with VHDL by William Clates. All these books are supporting books. Though I have placed Digital Fundamentals by Thomas Floyd as supporting book, but most of the topics will be covered from this book as well. So combinedly 1 and 2 you may consider as your textbook. I want all of you to collect the latest version of these books. Now let's begin the course. Digital circuits deal with digital logic circuit. The term logic is applied to circuits that operate on a set of just two elements with true value or false value. True means presence of the voltage and false means absence of voltage. So using voltage or current, we can represent our one state or zero state, that means true state or false state, or on state or off state. So what we understand by digital electronics that deals with logic high, that means presence of voltage or current, or this is the one state. Another state is logic low. If we convert it in terms of our electrical engineering methods, then this logic low says that it's absence of voltage or current. So generally this is represented by 1 and this is represented by 0. Presence of voltage, absence of voltage, or presence of current or absence of current. So all the computational methods must be converted in a way so that it can be represented by either 1 or 0. And we learned that digital electronics means these 1-0 things. As I told you that digital electronics mostly deal with designing of computers. And designing of computers, it all starts with numbers. So at the very beginning of this course, we'll cover the numbering system. So let me separate this part. We'll start with number system. In today's world, the most commonly used number system by the common human being is decimal system. Decimal system. Or we can say decimal number system. In decimal system, we have 10 distinct symbols or 10 decimal digits. For example, in decimal system, we use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These numbers are used to represent all the numbers. So each of these numbers are symbols. So how many distinct symbols are there? There are 10 distinct symbols. So using these 10 distinct symbols, we represent all the numbers. Well, these symbols are different for different language. For example, in Bangla, we have this one is represented by ek. This is 2, 3, 4, 5, 6, 7, 8, 9. So in Bangla, we have the same numbers of symbols, but it looks different than English. So it's nothing but symbol. And we have 10 symbols to represent all our numbers. So if we want to represent a number which is greater than 9, as we do not have more symbols, so what we do, we use or we utilize this existing symbol to represent the number beyond 9. For example, what is the next number? That is 10. So we use this two symbol, 1, oh, let me take English, 1 and 0. So after 9, the number that is used, we will use 1 and 0. We'll take help from these two symbols, and in this way we'll proceed. The next number will be 11. In this way we'll go up to 19. After that, if we want to represent our next number, again we'll use another symbol, that is 2 and 0. In this way we'll proceed. It may come into our mind that why do we use 10 symbols? We might use 9 symbols or 8 symbols to represent our numbers. For example, from 0, 1, 2, 3, 4, 5, 6, 7, 8. After 8, we may use 1, 0 to represent the next number. So in that case, we would have only 9 symbols. Why are we using 10 symbols, not 11, not 9, not 8? History says it came from the number of our fingers. For human being, we have 10 fingers. In the ancient days, people started counting using fingers. So they took 10 distinct symbols to represent the complete number system. And that is the decimal system. Well, there were some other civilizations on earlier days who used to use the number system other than the decimal number system. For example, the Babylonians numerals, they used to use 60 base number system, that means 60 symbols. Here I want to mention that the number of symbols that is used in any numbering system or any numeral system is called as base. Okay, so what is base? Base or radix, that is the number of symbols used in any system. Another numeral system which was used by the Maya civilization, you see, they used to use from 0 to 29, that means 30 symbols to represent their numbers. So for the Maya civilization, the base was 30. So for the decimal system, we have base or radix base or radix equal to 10. For Babylonian numerals, here we have base 60 that is written here, and for Maya civilization we have base 30. What does it mean? This single number represents 29 in our decimal system. So if we want to go beyond 29, we need to use these two symbols, 1 and 0. That means 1 means this dot sign and 0 means this symbol. I think it's quite similar to this, and this represents 1 0. If I convert the symbol to our decimal system, so this represents 1 and this represents 0. The value, the equivalent value of this number to our decimal system is after 29, that is 30. So this will be the 30 equivalent value in decimal. So this is the brief history of the number system that was used by the common human being, and currently the whole world is using this decimal system, which has base or radix equal to 10. So we have come to know about the most common number system used by the human being, that is decimal system, and it has base equal to 10. As I told you earlier, that computer uses two logic states, that is high or low, and these two logic states are represented by two distinct symbols, that is high means 1 and low means 0, and that can be represented by another number system which is widely named as binary system. Binary system. In binary number system, how many bases are there? As I told you, there are only two states, 1 and 0, so the number of base is 2. Now general people use decimal system and computer uses binary system. Whenever a general people uses a computer, we cannot force every person to learn binary system. So as an engineer, we must do something which will bridge between this decimal system and binary system. So the user will give the decimal input, that will be converted to binary, and all the internal calculations will be done in binary inside the computer, and then again it will be converted to decimal system to represent the output to the people, so that normal people understand the results. So we need to know the conversion between them. Conversion. There are other number systems which are used widely for designing computer systems. One is Octal System, that has base equal to 8. That means the symbols start from 0, then goes to 1, 2, 3, 4, 5, 6, 7. These are the symbols for octal system. So after 7, if we want to represent our next number, as we do not have any other symbols for octal system, so the next number will be 10, and the next number is 10. Here 10 in octal system means 8 in decimal system. Another system that is used widely, that is called hexadecimal system. Hexadecimal system, that has base equal to 16. So 16 base system. The symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here we have 10 symbols, but we need to have 16 distinct symbols. So the decimal 10 is represented by A in hexadecimal system. So A means 10 in decimal system, then B, C, D, E, F. Now, in order to have bridging between all the numbering systems, we need to know how to convert from one number system to another number system. Before we start that, we need to know how should we represent a number in this course. Representations of number systems. At the very beginning, if I ask you, what type of number is this? We cannot answer because this symbol represents hexadecimal number, octal number, and also decimal number. We are for sure that this is not binary number, but we cannot say definitely that what type of number is this unless or until we know the base or radix of this number. Well, normal people will say it is 75. That is in decimal, which is commonly used by human being. But in this course, as we are dealing with a lot of number systems, we cannot definitely say that this is decimal number. This may be decimal, or maybe octal, or maybe hexadecimal. That's why we need to know how to represent a number system. So whenever we'll write a number in this course, we'll say this is number symbol, and that will be closed by a bracket, and at the right bottom corner of the brackets we should write the number of radix or base. This is how we need to represent a number in this course in order to remove all sort of confusion. Now if we write this 75 and if we write 16 here, what type of number is this? This is hexadecimal because base is written here. Again, the same number 75 we are representing in this way, so this is decimal number. Again, the same number if we represent in this way, then the same number is octal number. So this is hexadecimal, this is decimal, and this is octal. Now, how a decimal number is represented? Suppose we have a decimal number 8653. This is the decimal number. This is the base. So this number has position. This is 0th position, number 1 position, 2 position, and 3rd position. So if we express this number as the sum of values of each digit, so this number can be represented by 8. 8 is the most significant digit. 8 into base to the power the position value, that is 3. In this way we need to proceed, we need to add. Then the next number is 6 into base to the power position value plus 5 into base to the power position value plus 3 into base to the power position value. In this way we can express this number as the sum of values of each digit. If we calculate this, we'll get 8653, and this is the decimal number. Now what's about the fraction? If we have 97,654.35, this is the 0th position, number 1 position, 2 position, 3 position, and 4th position. For the fractional number, as we go to right, we need to put minus and increase the value, -1, -2. In this way we need to proceed. So if we represent this number as the sum of values of each digit, so this number can be represented in this way: 9 into base to the power position value plus 7 into base means this is 10 base number, position value plus 6 into base to the power 2 plus 5 into base to the power 1 plus 4 into base to the power 0 plus 3 into base to the power -1 to represent this fractional number plus 5 into base to the power -2. This is how we express a number as the sum of values of each digit. We are concluding here. In the next lecture, we'll start with representation of other number systems, and we'll see how to convert from one number system to another number system. Thank you.